Good morning, good afternoon, good evening, good night, wherever you are watching this. Hopefully, this video finds you well. Hopefully, you're not panicking too much about organic chemistry. But if you are, you're in the right place. Let's talk about SN1 and SN2. So first, before we do anything, let's identify first our nucleophiles and our electrophiles. If you're confused on what those terms mean, go see my other videos about nucleophiles and electrophiles. But assuming that you guys are all caught up with that, I want you guys to take a second and pause the video and label what is the nucleophile, what's the electrophile between these two compounds right here. And I want you to do this for essentially every question that I ask to help get your brain going. Okay, so hopefully you identified that this is going to be your nucleophile, sodium bromide. This guy over here is going to be your electrophile, right? So your nucleophile is going to be the one that's going to be attacking your electrophile, yeah? And if you're confused about which is attacking and which is getting attacked, right? Just remember the root of nuke personally reminds me of the word nuclear weapons, or nuclear bombs, yeah? And even though this is kind of violent, right? But you know, there's a lot of science out there that says that the more vivid, the more violent the analogy, right? When it comes to learning, the more you're likely to remember it, right? And when you do with nuclear weapons, you attack with them. I mean, obviously, right? Hopefully, in the future, there's never a nuclear war, and hopefully, these weapons will never be used. But for the sake of organic chemistry, that's how I remember it, at least. And trust me, I don't like war like the next person in line, but this is just an analogy, okay? So between this nucleophile and this electrophile, right? I want you guys to also take a second to draw the product, right? If I threw these two into a cup with each other, or not a cup, sorry, a beaker. There you go. That's the chemistry term. What would be the product? You don't have to do any arrow pushing. Hopefully, you draw the product something like this. Okay, this is going to be your product. Product. Yeah. And so, a new key term that I want to introduce here, right, is that between these two right here, which is going to be your leaving group? If you said chlorine, that would be correct because your bromine would come in and replace the chlorine, and the chlorine would be kind of floating off on the side right here. If this confuses you, that chlorine is your leaving group, then you're in the right place. Let's talk about SN1 and SN2. Okay, cool. So SN1 and SN2 are basically the two main reactions the cornerstone reactions that from there all your knowledge of organic chemistry reactions will build on. And so let's first start with SN2 because SN2 is pretty easy, I would say, right? So let's say I had these two reactants here, right? SN2 is most importantly a very quick, very quick, usually one step reaction. So let's break down what SN2 does. Yeah. So in the first step, right? In the first step, the nucleophile, which if you guys want to take a second to guess, right, between these two, which is the nucleophile, which is the electrophile, it's going to be NaCl, right? And so that NaCl, right, is going to come in here. It's going to disassociate. Na plus is going to pop off on the side. And it's going to first do an attack. It's backside attack here, right? This first step is called backside attack. And then this causes a loss of the leaving group right here. Yep, just like that other example earlier, right? Your nucleophile is going to be attacking, and then something else is going to pop off in response. And that thing popping off in response is going to be the leaving group. Leaving group. Okay? And the second phase, right, is that you're going to draw your product something like this. Okay, cool. Let me just highlight this right here. And now, hopefully, right, you're kind of starting to, oh God, let me just quickly move these down, right? Hopefully you're starting to see here, right, that when you conduct an SN2, when you conduct SN2, what's going to happen, right, is that you take your nucleophile, right? You take that, and the thing that's going to be attacking is going to be the CL, right? Once that disassociates, your CL is going to, in this case, going to move attack into the backside right here. Something's going to pop off in response, and you're just going to end up replacing whatever you had before with your nucleophile. Make sense? Now you may be asking to yourself, wait, why did you draw lines here, but you drew a wedge here? Hopefully all of you are familiar with the concept of stereochemistry, right? And the difference between a dash and a wedge. But essentially, right, the backside attack will flip the stereochemistry of whatever thing you're attacking. So if it was a dash before, it becomes a wedge. If it's a wedge before, it'll become a dash over here, hypothetically. And so the second thing will be a switch of stereochemistry, right? Yeah. And all of this kind of happens in one step. I just kind of broke it down into two separate phases. This is the easiest way to understand SN2. Okay. So your nucleophile, right? Your NaCl will break off, go attack through the back. Br will pop off, right? Then Cl will take its place. Lit. Okay. Right. So this is kind of this is SN2. So sorry, I just moved my Zoom icon out of the way. Let's talk about SN1. SN1 is a little different, right? SN1 is actually kind of slow, and it's usually a multi-step reaction. If I had to summarize this, the golden rule of SN1, right, is that basically you'll find this out later, right? But any reaction that has multiple steps is basically SN1. So in this first step, right, the first thing that's going to happen, right, is not necessarily the attack, right? Nothing's going to be attacked just yet. The first step is actually something called the loss of leaving group, or LLG for short. Okay? So your first step here, this BR is going to pop off. And you're going to end up with this. The second step over here, right, is called the formation. Second phase is called the formation of carbocation. Yeah? Maybe this is a new term for you guys, but let me just break this down for you. Carb just means carbon, so anything with a carbon, right? Cation means plus. So carbocation basically just means any carbon structure that has a plus charge on it, which is what we drew right here. Then after the second phase is done, right? What's going to happen, right, is that you have your carbocation kind of just floating here. Yeah. And then from here, your nucleophile is going to come in. It's going to attack, right? So then your nucleophile, go ahead and highlight this right here. Attacks. Yeah, that's the step right there. There is important to know that this is not a backside attack. That is because, right, in this case, carbocations are usually flat. And when you're flat, it means that the nucleophile can attack from the top or the bottom. So what ends up happening, right, is that on your fourth final step right here, fourth thing that happens, you're going to have a mixture of stereochem. So you'll have structures that are like this, a wedge, plus structures that are like this. Okay. So just to recap, right? SN1 is basically a very slow multi-step reaction. Any reaction that has multiple steps usually can be considered SN1. First step is going to be your leaving group's going to pop off on its own. No need for anything to attack just yet. You'll form a carbocation, and then after that, the nucleophile will move to attack in. And since the carbocation is flat, it can attack from the top or the bottom. And then you end up forming a. Oh, I just realized. Whoops, what am I doing here? Why am I drawing Cl? My bad. It's gonna be OH. Sorry. Concept is the same. I just drew the wrong thing here. My bad. OH. You're gonna have this wedge and a dash. Yeah. So a mixture of things pointing up and a mixture of things pointing away from you. So these are the two reactions here, right? SN1, very quick. Everything happens in one step. You have a backside attack. The one step is composed of a backside attack and then the switch over stereochem, right? And then for SN1 over here, your leaving group pops off first. Then you have a formation of a carbocation. The nucleophile attacks, and then you get a mixture of things that are wedges or dash. Okay, cool. So with that being said, right, that was actually 10% of what you need to know, in my opinion, right? Because at the end of the day, you can memorize all the reaction patterns that you want, right? Because eventually, at the end of the day, it's just you applying reactants and drawing arrows to different types of reactants, right? But I think the most important part, right, is distinguishing whether or not you'll have an SN1 or SN2 given certain reactants in certain conditions, right? The biggest fight, I think 90% of the fight is just if I gave you, let's say, for example, reagent X and I put it in with reagent B and I put it under solvent A, what type of reaction will occur and what would be the product? Would it be SN1 or SN2? This 90% of the fight. So let's talk about, right, the different conditions that will facilitate SN1 or SN2. There's two main ones that I really want you guys to be aware of, right? So let me just go ahead and give myself some more space here because as you recall, I'm sure you all know, I'm the king of running out of space. So if you are ever in a situation, right, where your solvent is protic, yeah, we'll start off over here on this side first. Your solvent is protic, which means that your solvent is able to give off protons, right? If it was, for example, H2O, right? There's plenty of instances where H2O, right, where water can act as an acid, right, and give off its H's, right? Basically any protic solvent, right? Then it's going to be SN1. If you're a polar aprotic solvent, right, and hopefully you guys are familiar with your word prefixes, right? A means without. So if protic, we established that to be anything that kind of gives off H pluses, right? Like H2O. Aprotic means solvents that don't give off any H's. Stuff like acetone, right? Or DMSO. I don't remember what that looks like, but if you see DMSO, right? It's a polar aprotic solvent. If you see this on the bottom of any type of, if you see this on the bottom as a solvent, right, it's going to be SN2. So that's pretty easy enough, right? But what about these guys over here, right? What about if it's a secondary carbon or tertiary carbon or primary carbon, right? So let's break this down for you, okay? If you find yourself in a situation, right, where you are looking at different structures, I want you all to pay attention, right? First, identify the leaving group, right? What's going to leave in this scenario? So hopefully everyone identified the bromines, right? All these bromines will leave. Then I want you to find the carbon next to the leaving group. So from here, it would be right here, right? Because that's the carbon next to the leaving group. Be right here, here, and right here, right? I want you to then count the number of other carbons that are attached to it, right? So let's count this. I count one carbon here, two carbon here. This is going to be a secondary, right? And then I want you to count the ones over here. One, two, three. Going to be tertiary. And so essentially, right, we can keep on going for all of this, right? So I can count one, two here, secondary. If I count one right here, this is going to be a primary, right? And primary, secondary, tertiary, what? Well, the leaving groups pop off, they're going to form carbocations, right? So for example, if I took this, if I just redrew this over here, right? If this popped off, this would form a secondary carbocation. Okay? Form a secondary carbocation. And so on and so forth, right? If you pop off, right, it would form a primary carbocation. Yeah, if there's three carbons attached to it, form a tertiary carbocation. Hopefully you get the deal at this point, right? Now, the most important thing, right, is that if it's a primary carbocation, it's going to be SN2. No doubt about it. If it is tertiary carbocation, sorry, it's going to be SN1. If it's secondary, it could be either or. It could be SN1 or SN2. But you're going to have to need more. You're going to need more information in order to make that determination. Okay. So just to clarify, I'm just going to zoom out of this mess real quick. If you ever find yourself in a situation where you're given a bunch of reactants, but you don't know if it's going to be SN1 or SN2, first look at the solvent. If it's polar product, if it gives off H pluses, right, it's going to be SN1. If it's polar A product, it's going to be SN2. Okay. If you find yourself where there's a tertiary carbocation, right? If there's a leaving group pops as a tertiary carbocation, it's going to be SN1. If it's a primary carbocation, without a doubt, it's going to be SN2. But if it's secondary, it's going to vary between the two. Yeah, it depends on other conditions. Okay, let's look at some interesting examples here. Okay, so let's look at this first question right here. Right, so I see the solvent over here. That is a polar product solvent. Yeah, and so that is probably going to be SN1. But let's just triple check with everything else to make sure. So I want you guys to also try to figure out if this is a primary, if this will form a primary, secondary, or tertiary carbocation. Hopefully you all said secondary because I identify the carbon here next to the leaving group and I count one, two. So secondary carbocation. And we know from the chart above that SN1s can occur with secondary carbocations too. So what's going to happen? If you want to go ahead and follow my arrow pushing here, right? From Cl, the Br minus from the NaBr dissociating. This will pop off. We'll put this Br comes in here. End up with a mixture of these bad boys. Oops. Mixture of stereochemistry. In this case would be diastereomers. Okay, so just to recap, I looked at the solvents, I looked at the structure, and I decided this is going to be SN1. So the first one, SN1. Okay. Hopefully this color is legible. Nope, I'm not going to use that color. That's fine. Okay. In this case, no solvent is presented, but let's check the structure. Yeah. 1, 2, 3. Well, that's interesting, right? So given the only piece of data we can to discriminate between SN1 and SN2 is going to be the carbocation formation. It's going to be tertiary carbocation. There's no way that this could form, if this can do an SN2 attack, right? Because the logic behind this, right, is that tertiary carbocations, probably should have said this earlier, right? Very bulky. It's like, if I had to describe this, it would be like if you were a helicopter pilot and you needed to, I don't know, like drop off like a group of firefighters or just people, your passengers, right? In the middle of the forest or in the wilderness somewhere. if there was not a lot of branches blocking your way, you'd find it pretty easy to just go in, right? Hover a little bit, come down, drop your guys off, and then you fly off. Maximum 2, 3 minutes, right? However, if there's a bunch of branches in the way, right? For example, in this case, like carbons, I guess, there's a bunch of branches anyway, a bunch of debris, right? You're going to slow down, right? And so it's kind of like this, right? Your nucleophile will try to attack, right? But there's too many branches to attack. It's a helicopter pilot that's trying to land in the middle of a forest, right? If you can't land, right, quickly enough because there's too many branches and things in the way, other carbons, right? Then that's going to be SN1. So, with this being said, right, let's go ahead and let's execute this reaction. Yeah. So this will pop off, right? And then this will attack onto here. Then you'll get a mixture of this and this. This SN1 once more. Okay, cool. So let's move on to this second reaction here. Let's start third reaction here. And so, aha, we look at this, right? And this is acetone. Acetone is a polar aprotic solvent. And so what's going to happen here is that we're going to look at the structure, right? Let's confirm, right? I count one, I count two. This is going to be a secondary carbocation if formed. Okay, cool. And so what's going to happen is that add this here, right? Your CL is going to pop off, right? And remember, SN2 backside attack, everything happens in one step. And in this case, stereochemistry wasn't shown in the beginning, so it's just going to be Cl in this case. But if stereochemistry was shown, you're going to have to invert everything. Yeah? This was SN2. This right here. Okay. Let's move on to a bit of a trickier one, I would say. Right? So there's no exact solvent given here, right? But hopefully all of you recall that OH is a terrible leaving, which means that it can't pop off on its own in an SN2 attack, right? Because if you look at here above, right, this BR right here that was originally on here can just stand out on its own. Yeah. Pop off and then just kind of just, it can pop off on its own and then the CL comes in and attacks. Okay. And so this is a really good leaving group. BR is a really good leaving group. It can pop off on its own and that's okay. On top of that too, these guys are really good leaving groups as well. So how do we do this reaction, right? We've established that OH is a terrible leaving group. Well, the only other option, right, is to make OH a good leaving group. Hopefully this is jogging some memories for you. Luckily for us, right, we have HCl here. So what's going to happen, right? The first step is going to happen is that this OH over here is going to do a quick proton transfer. And you're going to get this. Let me go ahead and color this proton so it's easier for you to see. Right? So this OH right here is going to steal this H. And you're going to have a plus charge. Let's H2O here. Right? So this OH will become H2O. Now, one of the things that you should probably wrap your head around right now is the fact that compounds, elements, right? They generally don't like being plus or negatively charged, and they'll do everything in their power to alleviate themselves of that charge. That seems to be the common rule for this level of OChem, right? And so what's going to happen, right, is that this O is going to think to itself, oh my God, I'm positively charged. What do I have to do? I need to get out of here. So that OH is going to leave. H2O. It's happy H2O now, right? And you're left with this secondary carbocation here. Maybe thinking to yourself, okay, now maybe, right? Now it's time for us to move in and attack, right? That would be wrong. I've saved this little fun little exception for later, for the last question here. But essentially, right, if you can see here, right, there's a secondary carbocation here. But the thing is, right, when it comes to stability of carbocations, right, it goes in this order. Primary carbocations are the least stable. Secondaries are more stable. Tertiary is the most stable. If you have to do an SN1 reaction, right, please do a tertiary reaction. Maybe thinking to yourself, wait a second. Wait, how do we make this secondary carbocation into a tertiary one? Well, you're gonna have to do something called a hydrogen shift. So what's going to happen, right, is that hopefully all of you can wrap your head around this, but there's a hidden hydrogen here and a hidden hydrogen here. H, 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 and there's also another hydrogen here. Let me just move this plus charge real quick. King of running out of space. Oh yeah, H here. What's going to happen, right, is that I'm going to do a hydrogen shift onto here. You may be thinking to yourself, this is a really stupid exception. You're right, it is. Welcome to OChem, I guess. So what's going to happen, right, is that you're going to move that plus charge over here. And now this is a tertiary carbocation. And then from here, what was it, Cl. Cl you had from before comes in and attacks, and you end up with, oh my God, stop. You end up with a mix of Cl here plus wedges here. Okay, cool. Also led us to carbocation rearrangement. Yep. So hopefully this has been helpful, and please keep on studying, and I will see you all soon.